Welcome to DTH channel, lecture 2 in atomic and nuclear physics. This lecture is about detection of charged particles in fields like electric and magnetic field. I am going to organize this lecture in the following way. Introduction about detection of charged particles in the electric and magnetic fields. Then motion of a charged particle, some mathematical equations can be derived to understand the motion of a charged particle in electric and magnetic fields. Then J.J. Thomson's experiment, which is used to find the specific charge of an electron. Then Millikan's oil drop experiment. Finally, summary of the discussions we are going to have. Motion of a charged particle in the simultaneous presence of electric and magnetic field exhibit variety of paths ranging from the straight line motion, circular motion, and other complex paths will be traced by the charged particle if the electric and magnetic field are in different orientations. Both electric and magnetic fields impart acceleration to the charged particle. In this, the magnetic field imparts acceleration by changing only the direction of velocity, not the magnitude. Magnetic force being always perpendicular to the velocity vector of the particle, which tends to move the particle about a circular trajectory. So that's the nature of magnetic field when it acts on a charged particle. Coming to the nature of electric field when it acts on the charged particle, electric force is along electric field. So in which direction that electric field exists, the same direction electric force also will exist. This electric field is capable to bring about change in both magnitude and direction of velocity of the charged particle with respect to the electric field. If velocity and electric vectors are at an angle, then the particle follow a parabolic path. If the electric and magnetic fields are at 90 degrees to each other, then these fields are said to be cross fields. The specific charge of an electron could be calculated by applying the concept of presence of charged particles in the cross field, that is perpendicular electric and magnetic field. Now we will get into some mathematical calculations of the motion of charged particle in electric and magnetic field. For that, you assume a charged particle. That charged particle may be a positive charged particle. So this positive charged particle moves in a parallel electric and magnetic field. This is the electric field and this is the magnetic field. This positive charged particle has a velocity v. Assume that all the three are in x directions. So vx, ex, bx. So a positive charged particle having, this is the particle, positive charged particle having velocity component vx moves in a parallel electric and magnetic component ex and bx. Now there is no magnetic force because the motion of the charged particle and the direction of magnetic field are in the same direction. So there is no magnetic force. There is no magnetic force in the sense the magnetic force is 0. That means Fm is equal to initial velocity of the positive charged particle and into charge of the positive charged particle and the magnetic field, then sine component, perpendicular component or vertical component of the magnetic field. Here there is no angle between the velocity of the particle and magnetic field of the particle. So sine 0, which is equal to 0. So the magnetic force is 0. Here Next, come to the electric field. The electric field accelerates or decelerates the charged particle based on the polarity of the charged particle. Considering a positive charged particle, the electric field will produce a force of Fe is equal to QE. So, the product of charge of the particle and the electric field will give the electric force acting on the charged particle. You can calculate the acceleration of the charged particle due to electric field in the x direction. Since the charged particle is moving in the direction of magnetic field, there is no magnetic force, but electric force is there. That electric force imparts an acceleration. That acceleration is A is equal to the force due to electric field and mass of the charged particle. The force due to electric field is nothing but QE, we know that, QE by m. Now, you have calculated, you learnt the acceleration in the x direction. From this acceleration, you can find the displacement along the x direction in time t. Displacement of the charged particle in the x direction in time t. For that, you have to bring the equations of motion, one of the equations of motion. You know that displacement equation is S is equal to ut plus half at square. Rewriting that equation to fit into this situation, we can get x is equal to v naught t plus half a suffix y t square. So, you got substitute the value of this a. So, x is equal to v naught t plus q e by 2 m into t square. We are substituting the value of this acceleration in this equation. So, that equation becomes x is equal to v naught t plus q e t square by 2 m. This is the position of a positive charged particle in x direction after time t. Here we learnt that when the charged particle is moving in a parallel electric and magnetic field, all the three are in same direction, that is velocity of the charged particle, electric field, magnetic field, all the three are in same direction. Now, we are going to do the next situation. The next situation is the electric and magnetic field are perpendicular to the velocity vector of the charged particle. For that, you need to understand the coordinate system. So, this is the coordinate system, this is x direction, and this one is y direction, and this one is z direction. Here, electric field and magnetic field are along y direction. This is the electric field, and this one is the magnetic field, electric field and magnetic field. Now, initial velocity of the charged particle is v naught. Initial velocity of the charged particle is v naught. That velocity is along the x axis. This is the direction of velocity of the charged particle. Now, applying right hand vector cross product rule, we determine that the magnetic force is in the z direction. The magnetic force is in the z direction. So, this is z direction. The force due to magnetic field will be along the z direction. If the electric field is not present, what happens is the particle exhibits only the circular motion. So, this is the circular motion of the charged particle. So, it starts here and moves here, and it goes around and comes and completes a circular motion. So, if you draw a tangent to the circle, that will give the velocity of the charged particle at that instant. So, from this what you learnt is, if a charged particle is moving perpendicular to both electric and magnetic field, then it will exhibit a circular motion. Here it is assumed that if the electric field is not present, only magnetic field present, then the charged particle will trace a circular path. Now let us come to the situation where both electric field and magnetic field. So for that, again you go to the coordinate system. This is x axis and this is z axis and this is y axis. Here electric field and magnetic field are in this is the magnetic field and this is the electric field. Then the magnetic force is in z direction, magnetic force is in z direction. In earlier case we have switched off the electric field. Now we are going to switch on the electric field. Once that electric field is switched on, the path traced by the particle, positively charged particle, the path traced by the positively charged particle will be like this. It will exhibit a cycloid. So electric field will accelerate the particle in y direction. So like that, cycloid path will be traced by the charged particle. The gap between the distance between two cycloid is due to the magnitude of the electric field. The distance between the two cycloid is based on the magnitude of the electric field, because magnetic field makes the particle to move in a circular path. Electric field makes the particle to move in y direction. So you will get a cycloid path. So based on the magnitude and direction of electric and magnetic field, you can find different paths for a charged particle. Radius of the path traced by the charged particle r is equal to v by alpha b, where alpha is the specific charge of the charged particle. Specific charge of the charged particle, E by m. Specific charge of an electron was determined by J.J. Thomson using his experiment, Thomson's parabola method. We are going to see that Thomson parabola method next. Then time period taken by the charged particle to complete one rotation, t is equal to 2 pi by alpha beta. Then frequency of the charged particle, nu is equal to alpha specific charge times the magnetic field into divided by 2 pi. So this is the time period, frequency of the motion of the charged particle. Then angular frequency omega is equal to alpha b. This is the angular frequency of the charged particle. So like this you can learn many terms if a charged particle is moving in angular frequency, is moving in a combined electric and magnetic field. This concept is used in understanding the J.J. Thomson experiment, which is used to calculate the E by m of electron. This is the apparatus setup of J.J. Thomson. In the first part, cathode is placed. Then through anode, positive rays are streamed through the apparatus. Then anode is there. That anode is used to attract the rays which is entering into the evacuated chamber. Here you can see two electric plates, horizontally placed electric plates, which is used to provide electric field in the apparatus, electric field in the experiment. Then two electromagnet, south pole and north pole. These two are employed to give magnetic field to the charged particle. So this electric field and magnetic field are perpendicular to each other. So cross fields are given here. Then the deflected charged particle will hit the fluorescent screen placed at the end of the chamber. Based on the position of the fluorescent chamber, distance between two spots, based on the position of the fluorescent chamber, distance between two parts, we can calculate the E by m of an electron. So this is the apparatus setup used by J.J. Thomson. Now come to some calculations in this J.J. Thomson experiment. Imagine that electron is entering into the electric field plates. So this is the electric field plates. You can see here this electric field. The length of this electric field is L, and the distance traversed by the electron is S. So how much time it takes to traverse this distance? These concepts are used to calculate the E by m of the electron. Assume that electron is moving in the positive x direction, Electric and magnetic field are applied to the electron. So electric force will be there, magnetic force will be there. Electric force Fe is equal to Ee, then magnetic force Fh is equal to minus EVH, where V, small e is the charge of the electron, and capital E is the electric field, small v is the velocity of the electron, then this H is the magnetic field. These two forces are same. Then what happens to the electron? That electron will not deviate from its path. So these two forces will be equal. Then you will get the net force as Fe plus Fh is equal to 0. Substituting the value of electric force and magnetic force, you will get Ee minus EVH is equal to 0. Rearranging this equation, we will get the velocity of the electrons entering into the electric field will be E by H. So this idea is used as velocity selector for the electrons to enter into the experimental space. So certain velocity electrons alone will be allowed. Now switch off the magnetic field, hence only electric field alone will be there. So the charge carriers can be deflected by the force. This provides that charge carriers are fundamental in nature. If they are fundamental in nature, they will get mass and charge. So the charge particle entered into the experimental space as mass and nature. So its specific charge can be calculated. Now we will use the specific charge concept. Position of the electron x of t is equal to Vt, which is equal to the velocity of the electron into time. This is the x position of electron as a function of time. Now acceleration, this gives a constant force, gives rise to acceleration. A is equal to Fe by m. So coming to the y position, y of t is equal to half at square. This is the y position. Now substituting the value of this acceleration here, this equation will change to half into electric force by m into t square. Rearranging this equation, you can get E by 2m t square. Now the electric field is turned on such that this is the y position when the electric field is switched off. Now we are going to switch on the electric field. Once that electric field is switched on, what happens is the distance traveled by the electron will be to hit the positive plate. So this is the distance S. So this is the length of the electric field. So L, the length is equal to velocity into time. So velocity is nothing but E by H into t. Then t is equal to HL by E. So this time will be taken by the velocity selector. This is also the time required to travel the distance S. So what happens is y of t is equal to E by 2m into t square. So S is equal to E by 2m into LH by E the whole square. So this is the distance traversed by the electron by knowing the length of the electric field plate and magnetic field and electric field. Rearranging this equation, we will get the E by m value of the electron as E by m is equal to 2s by E into E square by L square into H square, which is equal to E by m is equal to 2SE by L square into H square. This is how Thomson's parabola method is used to calculate the E by m of the charged particle. Today's accepted value of this E by m of electron is 1.7588 into 10 power 11 coulomb per kilogram. So this is the E by m value of the electron. Now we will do a problem based on this Thomson's parabola method. The problem is the DC voltage applied to accelerate particle between cathode and anode and the DC voltage applied to the plates to produce electric field perpendicular to electron beams are equal in the Thomson's experimental setup. If each of the two DC voltage as applied are doubled, then by what factor should the magnetic field be changed to keep the electron beam undeflected? That is the question based on Thomson's parabola method. Answer for this question can be obtained by knowing the specific charge of an electron. Alpha is equal to E by m, which is equal to E1 square by 2V1 B1 square. Here E1 is the electric field initially applied. Then in the question it is said that this electric field is doubled. If each of the two DC voltages as applied are doubled, then by what factor should the magnetic field be changed to keep the electron beam undeflected? So you have to convert this electric field into potential. Electric field and potential relation is E1 is equal to V by D, where V is the potential. You can keep this as V1 and D. Then alpha is equal to V1 by 2D square into B1 square. This is the specific charge. Here we are going to apply a new electric field to change that. So B2 is the new magnetic field when two potential differences applied. So V2 is equal to 2V1. Hence alpha is equal to 2V1 by 2D square B2 square, 2D square B2 square. Combining the two equations we will get, because in the question it is said that for the beam to undeflected, 2V1 by 2D square B2 square is equal to V1 by 2D square B1 square. If you rearrange this equation, we will get 2V1 D square B2 square is equal to 4V1 D square B1 square. So B2 square by B1 square is equal to 2. So B2 by B1 is equal to root 2. So the new magnetic field to be applied should be root 2 times the old magnetic field. This is the answer for this question. So like this you can do many problems based on the J.J. Thomson's experiment. The next experiment is Millikan's oil drop experiment, which is very useful to find the charge of an electron. So this is the apparatus setup. In this apparatus setup you can see steel tank, brass pressure sealed vessel up to 15 atmosphere. Then this is the mercury manometer acting as a standard barometer at atmospheric pressure. Then these two are that plates M and N condenser plates and glass with G3. So this is how the Millikan's oil drop experiment. Millikan's oil drop experiment is used to find the E by m of electron. Initially Millikan used water, but he found that water quickly evaporated. Then based on his research scholars, his student idea, he used oil drop. Then Millikan first measured the oil drops with no charge. Here two forces act upon the drop in the scenario. This is the Fg is equal to 4 by 3 pi r cube rho minus rho r, and the viscous force is equal to 6 eta r Vt. These are the two forces acting on the oil drop, where r is the radius of the droplet, g is the acceleration due to gravity, rho is the density, eta is the viscosity of air. Here you can see the free body diagram of an oil drop which is in free fall. The gravitational force is acting downwards, then the viscous force is acting upwards. Only two forces are acting here. In this case, the terminal velocity f b is equal to f g if there is no field is applied. Then the radius of the oil drop R2 is equal to this one. By measuring V, we can find that. Next, Millikan observed the droplets with charge. So the charge is applied using X-ray in that thing. What happens is the terminal velocity is 0. The velocity is 0. Now, adjusting the electric field between the plates, we can cause the droplet to rise, fall faster, or even stop moving entirely. So the electric field and is equal to QE. D is the distance between the two plates. Now Fe is equal to Fg. Electric field is equal to electric force is equal to gravitational force, so that the oil drop can remain stable. Millikan observed that and he found that the total force Fe is equal to Fg plus Fe. So he got the charge as Q is equal to 6 pi eta r Vt plus Vr d divided by V. He measured 58 droplets over the course of 60 consecutive days, collecting all the 60 cases, and he found the charge of an electron. By comparing the differences of charge between each droplet, Millikan was able to determine that charge of the droplet was always an integer multiple of a minimum charge, the charge of the electron. He found that charge of the electron as 1.592 into 10 power minus 19 coulombs. These values were drawn with such precision that the experiment was not improved upon for several 2 years. His calculations are within 1% of today's current accepted value of the electron charge. So Millikan experiment paved a very important role in the discovery of the charge of an electron. So in this lecture, we have learnt the motion of a charged particle in the simultaneous electric and magnetic field, J.J. Thomson's experiment to find the E by m of electron. In that experiment, you learnt that the accepted value of E by m is 1.7588196 into 10 power 11 coulombs per kilogram. Then Millikan's oil drop experiment. In that Millikan's oil drop experiment, charge of an electron is determined. It is found that 1.592 into 10 power minus 19 coulomb. These are the things we learned from this lecture. You can learn more about this concept by surfing through this website.